You know, we trust things every single day without a second thought. An elevator, a bridge, a stadium. We just assume it's all rock solid. But what if all that security, all that safety, hangs on a single, small component working under just immense pressure? Well, today, we're pulling back the curtain on one of engineering's true unsung heroes.
Now, really think about that for a second. In an elevator, the entire system, we're talking the motor, the guide rails, the car itself, is anchored directly to a concrete shaft. So what's actually bearing all that weight and all that force? The cables, the electronics, or is it something else entirely? Well, the answer is surprisingly simple and unbelievably strong. All right, so here's the game plan. We're going to start with the component itself, then we'll dive into the three main ways it works. From there, we'll get into the science of making it secure, how it's all put into practice, and finally, why it's the absolute foundation of safety. So that critical link, the unsung hero holding these massive steel structures to solid concrete, it's the humble but oh so mighty anchor bolt. Think of an anchor bolt as the ultimate middleman. It has to take every single force from that steel structure, pulling, pushing, sideways shear, and transfer it deep into the building's concrete foundation. I mean, without this vital connection, nothing stays put. It is quite literally the handshake between steel and concrete. But here's where it gets really interesting. Not all anchor bolts are the same. They get their incredible grip in three totally different ways. It's almost like they have three distinct personalities. One that uses friction, one that creates a physical lock, and one that acts like a kind of industrial superglue. The first, and maybe the most common type you'll see, relies on pure friction. You'll often hear these called expansion anchors. The concept here is just brilliantly simple. As you tighten the bolt, a sleeve or a wedge down at the bottom expands, and it forces itself against the walls of the hole. This creates this enormous frictional force, so much force that the bolt is almost impossible to pull out. It's just pure brute force grip. But like with anything in engineering, right, there are trade-offs. The huge advantage here is speed. They're incredibly fast to install, and there's no waiting around for anything to cure. The risk, though? Constant vibration, like from an elevator going up and down, can potentially cause them to loosen over time. And their grip also depends heavily on the quality of the concrete itself. So what if you don't want to rely just on friction? Well, the next type of anchor doesn't just grip, it physically locks itself into place. These are what we call mechanical interlock anchors. Yeah, so instead of just friction, this type uses its own shape to create a physical barrier. Imagine a J-shaped hook or a bolt with a huge head on the end, and it's embedded deep inside the concrete. Once that concrete hardens around it, you literally can't pull the bolt out without destroying the concrete itself. It is mechanically locked in. Now, this approach gives them incredible pulling strength, and they actually perform really well even in concrete that might have minor cracks. But the trade-off is in flexibility. The installation is more complex, they have to be set much deeper into the concrete, and once they're in, they are in for good. There are no adjustments possible. And that brings us to our third type, the really high-tech option, the adhesive or chemical anchor. This approach is a total game changer. Instead of relying on friction or shape, it uses pure chemistry. A hole is drilled, cleaned meticulously, and I mean meticulously, and then it's injected with a high-strength resin. The anchor is pushed into the resin, and when it cures, it creates this single solid structure, bonding the steel to the concrete on a molecular level. When it comes to pure performance, man, these are the heavy hitters. They are fantastic for dynamic loads, which makes them perfect for an elevator, and they distribute stress beautifully. The catch, and it's a big one, they demand absolute perfection during installation. They need time to cure, and their strength depends completely on the temperature and, most importantly, on how clean that hole is. Even a tiny bit of dust can compromise the entire bond. So you see, choosing between friction, lock, and glue, it's not just, a matter of preference. It's a complex engineering decision because the forces involved are just immense, and the consequences of failure are, well, they're severe. And this is the exact question that keeps engineers up at night. It's not enough to hope an anchor holds. You have to anticipate, you have to calculate, and you have to design against every single way it could possibly fail. So what can actually go wrong? A connection can fail in a surprising number of ways. The steel bolt itself could just snap under the load. A cone of concrete could literally break away from the surface. The anchor could just slip right out, or the chemical bond could give way.
And if it's too close to an edge, that edge could just break right off. Every one of those is a distinct failure mode that engineers have to prevent.
So, how do they stop this from happening? Well, this is where the real science kicks in. Engineers use these incredibly detailed formulas from industry standards like ACI 318, which is basically a rulebook built from decades of research and learning, to calculate the anchor's strength against every single one of those failure modes. They factor in everything: concrete strength, bolt diameter, how deep it's embedded, how far it is from an edge, all to ensure a massive margin of safety.
Okay, so a perfect design on paper is one thing, but it's totally worthless without perfect execution on site. The installation phase is where that engineering blueprint becomes real-world safety.
To make sure that design becomes a reality, there are 4 steps that they're absolutely non-negotiable. The hole has to be the exact depth required. It has to be cleaned perfectly, especially for those adhesives. The bolt needs to be tightened to a precise torque value to get the mechanism to engage correctly. And for critical systems like elevators, installers will even conduct on-site tests, pulling on the anchor just to prove it can hold the calculated load.
So after all that, the different types, the science, the nitty-gritty installation details, what's the big takeaway here? Well, it all comes down to trust. Trust that is built entirely on a foundation of deep, specialized expertise.
This is really where specialists make all the difference. The experts at Novempuya Elevator, who we consulted for this explainer, put it perfectly. For them, designing and installing every single connection to the most rigorous standards isn't just a goal, it's the core guarantee of safety and stability. So what does this all mean for you? Well, ultimately, the next time you step into an elevator, you're not just trusting the machinery. You're trusting the meticulous calculations and the expert installation of every single anchor bolt holding it in place. That invisible connection is the very foundation of your safety, and it's built entirely on engineering expertise. It kind of leaves us with one last thought, doesn't it? In a world of these massive, complex systems, is it really true that a structure is only as strong as its smallest, most overlooked connection? Something to think about the next time you step into an elevator.